Okay, good afternoon everybody, and welcome to the last session in Stream 3. Hopefully you're here to hear about industrial control system security. After this session, I think we're all moving back into probably Stream 1, or 2, and the final sessions will be completed in those ones at the end of that. If there are any questions, if you wait till the end, and then if you raise your hand, we'll bring one of the roving mics round so that people can hear the question, and also it gets captured on the recording. And also just to remind you that there is the bookshop next door. There's a silent auction going on for some of the books in there to raise money for Bernardo's. So if you're interested in that and haven't done that already, then make sure you have a go at that before the end of the day. But I'll hand over to Peter Hazel now. So Peter spent a lifetime working in this area, and he was saying earlier, everything from sweeping the floors right through to running his own company, and he's going to share some of his experiences and thoughts around ICS security. So I'll hand over to Peter now.
Thank you everybody for attending. It makes it all worthwhile a little bit. That's me. The only thing really you need to know about me other than that is I started as a trainee instrumentation technician in the late 70s, which was just when the very first computerization of process control started. Before then it was all electromagnetic, pneumatic, etc. So I've really sort of seen this industry grow. In the mid-1990s, the control system, industrial control system world started opening up, and we started networking the computers, and it was at that point that I started getting interested in security. And it's something I'm quite passionate about, so if I get overexcited, I apologize in advance. Right, what I'd like to talk about, very quick introduction. I'd like also to look at very briefly at risk, and then concentrate on industry structure and what is a process industrial control system, because a lot of people get a bit confused with that, and then pull it all together and see how the industry structure and the control system architecture work against you or for you from a security point of view. So, I'd like to ask two questions for you to consider while I'm talking. First of which, because I guess most of you come from an InfoSec world, what is the value of information in the world of process control? And the other one that I'd like to ask you and for you to consider, could the power grid or the North Sea oil production be brought to a standstill by a cyber attack launched against power stations or production platforms? Because, you know, the sort of doom mongers of this world always focus on, well, what happens if somebody attacks power stations? And I think you might be surprised to find that the risks aren't what you might think they were. Right. So quick look at likelihood and consequences, in other words, risk. Well, again, there are an awful lot of horror stories about industrial control system security. But compared to other computer systems, control systems are actually quite difficult targets. Generally, if you can get close enough to an industrial control system to compromise it, there are probably better ways of taking the plant out. And I quote Little Barford, when we were building that, they didn't bother with the control system, they just drove 6-inch nails through power cables and control cables, and it cost millions to put right, and it delayed the project probably by about 8 months. Operators in industrial plants are used to unexpected outages. On some of our old aging fleet of power stations, you'll be surprised, they're shut down probably about 2 weekends out of every 4 having boiler tube leaks fixed. So in that context, a cyber attack might not be as serious as it might be for a bank or something else. Also, in terms of incident response, from an engineering perspective, we're fairly well rehearsed in that. In fact, if you shut a plant down, what happens is there's a mad scramble for permits. So if you have a turbine which suddenly trips for an unexpected reason, somebody says, well, the plant's going to be out for 6 hours, everybody who thinks they can get a maintenance task done in under 6 hours will be scrambling around trying to get permits to get that work done. So in fact, you might find that the initial shutdown condition is sorted after 6 hours, but they only bring the plant up 12 hours later. But what that does mean is that they don't have to shut the plant down again in 2 weeks' time to do those routine mechanical maintenance things. Historically, there have been very few targeted attacks against industrial control systems. Now, I use the word targeted. We do use Windows systems, so they're still vulnerable to things like ransomware, etc., etc. But there have been very few targeted attacks actually against the industrial control system. And they tend to fall into three categories. Employers with detailed engineering knowledge, who are generally acting fraudulently. Now again, going back to the day, back in the 1980s, there was a renowned contractor working associated with what I was doing, who was routinely setting a timer in a PLC, effectively a PLC. He knew what day and time it was going to fail, and he always made sure at that night he was at home and he was sober. And surprise, surprise, he got called out, overtime rates, got paid a fortune to go and fix a bug that he'd put in. In those days, it was just treated as something naughty. In a company I've been associated with recently, somebody did a similar thing, and it's considered a cyber attack. And at what point in that 20-year period has something which was just something naughty become a cyber attack? Well, I'll leave you to judge that one. Then you get the disgruntled ex or not so ex-employees, again with detailed engineering knowledge of the plant, with access to the control system, who does something naughty. And the story there that everybody's probably aware of is in Australia, the release of sewage from a water company. And then you get the sophisticated attacks, and they're looking to damage a plant. And I introduced this term EDOS, Extended Denial of Service. That's where the primary target isn't the computer system, it's a mechanical asset. Because you can take a computer system down with a virus or whatever, you can probably have it up and running within 12 hours. And those people who, from the InfoSec world, probably familiar with that. If you take out a 2 megawatt feed water pump on a power station, which is an absolutely key bit of kit, it's going to take you a minimum of 12 weeks to get that rewound and back in service. So if you can take them both out, you shut down, well, not the entire power station, but you shut down one unit, typically about a quarter of the power station, and it's going to be out for sort of 16 weeks. So that one, if you look at that, the famous one there, of course, is Stuxnet, which you've all no doubt heard about. So I say the likelihood of an attack is quite remote, reasonably. So can we ignore it? Few conceptual things. Conceptually, unlike an IT system, a control system should be viewed just as another component in a mechanical plant. So it should be viewed as like a pump, piece of switchgear or something like that. We had mechanical plant long before we had computer systems. If you compare that with the InfoSec world, we didn't have email before we had computer systems. So we have to consider conceptually, just see the computer system as being another component in the process. The other thing that's important to consider are the generic risks. InfoSec talk about CIA. We talk about pair. People, that's safety, the environment, the asset, we touched on that with Stuxnet, and reputation. And if you don't think reputation is important, I'd just like to remind you Thames Water's been fined £20 million for putting sewage in the Thames, so it is quite important. So the consequences, although the vulnerabilities are quite low, the consequences of cyber attack are quite high. I mean, you've got to consider, these obviously aren't cyber attacks, but it's where we get it wrong in the process industry. Bhopal, 2,500 to 6,000 deaths, 200,000 long-term health problems. Piper Alpha, 167 people killed. Deepwater Horizon, Thames Water again. And then another EDOS attack against Ohio water treatment. Again, that is very akin to the feed water pump. Big pumps are on limited starts an hour, generally 3 starts an hour. If you cycle them on and off, they tend to burn out. And that's what they did at Ohio. So can we also answer the first question? What is the value of information in the process world of process control? Any ideas? Any? Into secret. 0. Information, and we'll come on to what I mean by process control industry in a minute. Information doesn't mean anything. It has no value. Generally, there might be exceptions, and although it's not strictly a process industry, the pharmaceutical industry would be one, because they keep the recipe for their drugs on the control system. But that's a batch process. So if you have a new drug and you access a control system, you can find out how that new drug is made. But that's really outside of the scope of the type of control system we're talking about today. Okay, except in the aid of an extended denial of service or EDOS attack. You can have 100% access to a industrial control system. What are you going to do? How are you going to know what bit of plant to attack to disable that plant? Well, as I'll explain later, all of the engineering information you need to make those decisions are stored on a control system. So if you can have access, you can load those up, you can then figure out exactly which bit of the plant you want to target on an EDOS attack. Okay. The other thing is the information security. The InfoSec rulebook is not particularly relevant in this space, and we'll get on to why later on. Right, leads to two important, I think we basically covered this. We've got two conceptual differences between the two types of security. OT, that's operational technology, control systems. IT is information technology. So, industry structure. This is quite an important topic because, again, it helps you evaluate risk. Computer systems typically split into information technology and operational technology. We're considering operational technology. And it's dangerous. I feel it's dangerous to assume that competency in the IT world automatically translates into the OT world. And incidentally, there are more published cases of production plant being brought down and production halted or reduced by inappropriate InfoSec countermeasures than there have ever by hackers. And if you don't believe me, there were 3 control systems that the upgrade from Windows XP Service Pack 2 to 3 brought them to some form of standstill one way or another, from one which completely stopped it operating to the other which stopped the any engineering changes being made. So there were 3 control systems that never went beyond XP Service Pack 2. Right, so what do we talk about operational technology? Well, we've got several types. We've got process, batch, manufacturing, transport, distribution networks, and others. And they share many of the same technologies, PLC, SCADAs, field bus, etc. The ones I'm interested in, if risk is, it's also risky. If it's risky to transfer knowledge from the IT world to the OT world, it's also quite risky to move them across these. And this is why I'm going to be sticking in this area, which is the area I know well. And that's petrochem, oil and gas, power, water, and other process industries. And the other thing that they're having, 3 of those have in common, they also have distribution networks, which is very much a space I'm working in at the moment. I'm working in telemetry, which is basically the bit of string that glues what happens at the plant level up with what happens at the IT level. So again, they use some of the same technologies. The important thing, the facilities are organized and run and managed in very similar ways. You can move from an engineer, you can move very easily from the power to the petrochem, etc. And it's the same in the security world. And they're also subject to, at an operational level, to the same sort of regulations. So we have things like DSIR, which is dangerous substance and explosive environment regulation. They cut across there. There's a whole lot of them, so I won't bore you with that. Right. So we looked at the industry structure. Now the question is, what is a process industrial control system. And this is a generic model, and it holds up pretty well for any industrial control system you like to look at. And it's split into 3 levels. At the bottom, there's the field or the instrumentation level. In the middle, there's the automation level, and at the top, there's the supervisory level. And if I can get this to work, you will notice off the supervisory level, there's a little arrow there off-site to your management information systems. Beauty of this is you can draw a box around it. A lot of people know who touch in this area know about the supervisory level. A lot of you have heard about PLCs. If you're talking about PLC SCADA, DCSs, we have a similar thing here. We just call it something different. And we also have emergency shutdown, programmable emergency shutdown systems in at this level. But the thing that always gets missed is this level down here. There's a huge range of intelligent and programmable devices, actually at a field level, which people are on the whole completely unaware of and never consider. So this is the definition of an industrial control system. It's any programmable equipment which is used in the collection of data from the field or the operation of the final element. So we're talking about the instrumentation layer. In the control manipulation of the final element, so we're talking about the automation layer. In relaying or displaying plant status information to plant to operator or other staff, so we're looking there at the supervisory layer. The communication of data between any of the above. Industrial control systems rely very, very heavily on different communication protocols, none of which are at TCP/IP, incidentally. And the last one is very, very important because going back to the difference between CIA and PAIR, the industry has been managing the PAIR risk for decades, longer than the industrial control. The computer world has really existed, and they have got very, very good tools for managing process risk. And probably heard of it, the Swiss cheese model. We talk about layers of protection. So if there's a hazardous process, we might have the PLC does some protection. There might be some mechanical interlocks which do some other protection, and you might even have an emergency shutdown system bolted onto it. Each one is completely independent, and they all are analyzed based on random failure rates. So we can use the Swiss cheese model. You can't use that when you consider an attack, because an attack is a targeted thing. The Swiss cheese model relies on Pascalian statistics, and it only works when you consider random failures. But the point is, if there's anything that is used as a layer of protection to protect the safety critical part of the plant, it has to be considered in this analysis, or the analysis of risk, cyber risk, and it's not always obvious that some of these devices exist. So we'll come back to this model, and I've just included, if you go back, if you look at the numbers down the left, I've put them in as clause, the little C's, so they relate up to that last slide if you're interested. Right, so we're going to look at the field and instrumentation layer. Right, here's a piece of pipeline, and it's got some instruments on it. Starting at the left, you've got switches. There's nothing clever about a switch. It's just that, 24 volt, typically 24 volt powered. It's either open or closed. Pneumatic valves are the same. There's nothing programmable about them. But transmitters, these are things which measure pressure, flow, temperature, etc. They generally have some intelligence built into them. And so do motorized valves. They have some intelligence, they're programmable. And so do modulating valves. Modulating valves are valves you use to control the pressure or temperature, so they're not fully open or closed, they're somewhere in between, and they change their position to regulate something. And then on the right-hand side, you have MCCs, which stands for motor control centers, or VSDs, variable speed drives, otherwise known as inverters, etc. That incidentally what was targeted on Stuxnet was a VSD. So if you look at the bottom line, just look at the instrumentation, the vulnerability from a cyber point of view starts at very low on the left-hand side and gets progressively higher as you move to the right. And if you look at above that, we have various ways that we can transmit that information from a field level to the automation level. We can either do it on wires, 4 to 20 milliamps, 0 to 24 volts, depending on whether it's analog or digital. Nothing really you can attack on the cyber level from that. But we do have wireless connections. They're quite vulnerable. There are incidentally two wireless standards. There's wireless HART and there's ISA 99. I've done an analysis of 99 from a security point of view, and it's very, very like Bluetooth on an industrial scale. And there's HART as well, and HART is a digital protocol that is superimposed on the 4 to 20 milliamp signal. And there are various articles on the internet which will tell you that from a CIA point of view, HART is terribly, terribly vulnerable, etc. But whether or not that equates to risk depends on something we'll speak about later. So the field level, it's generally protected by good physical security. We'll get onto that later. Many articles covering this technology confuse vulnerability with risk. Yes, from a cyber point of view, they are probably vulnerable, but you have to get to them first. And as I say, we go back to the little Barford and driving nails through cables incident. And they're difficult to compromise externally. A lot of the instrumentation stuff is built into instrumentation, unless you embed it in embed it into the valve or transmitter when it's manufactured, which is a possibility depending on which country it's been manufactured in. But generally, it's fairly low risk. And we move up one layer to the automation layer. These are PLCs, RTUs, nodes, processors are depending. The terminology, PLCs, you talk about PLCs with SCADA, RTUs, nodes, etc., is when you talk about what are called distributed control systems. The architecture is the same. The distributed control systems tend to be better integrated from top to bottom. But the important things to note is we've got lots and lots of communications. You can have TCP/IP, but it's unusual. But we have things like Modbus, Profibus, AB485. They're literally dozens and dozens and dozens of different protocols used in the industrial control world. We have digital inputs, digital outputs, analog inputs and analog outputs, and they connect down to the field level. You also, one thing we haven't touched on is you also have some slightly offbeat ways of measuring temperature, which have very specific electrical characteristics. And then on the left you have a processor card or two processor cards, depending on whether it's a redundant system or not, and we'll look at those in detail in a minute. You can also have remote I/O. So this is where the I/O cards are connected by an industrial protocol, communications protocol, and a rack. These are physical 19-inch racks, and this is mounted out in the field. So if you can imagine a control system which has 1,000 I/O, and you've got to wire all of that I/O back on twisted pair from the field a kilometre away, that has a huge cost. It then becomes worth your while to remove the I/O and actually put it closer out into the field where the instruments are and connect it with a communications bus and bring the data back. Of course, communication buses are potentially vulnerable, and this device may be outside of the physical security of a site. So if we look at the processors, and again, those from an InfoSec world, these are quite different animals. They're static. You develop the software offline, you download it. Once it's up and running, commissioned, you don't touch it. I've known some of these processors which have been left for years and never ever had the software changed in them. They have no hard disks. It's all direct memory addressing. So there's no way of sort of putting layers of stuff in and all the sort of thing you get, all the vulnerabilities you get in Windows from that point of view. Their operating system is firmware based. Now in the good old days that used to be on an EEPROM. So it meant if you needed to change it, you had to take it out, put it in a UV oven for a quarter of an hour and then reprogram it. Nowadays quite a lot of that is on flash. And some control systems will allow you to download a new version of firmware from the engineering workstation up at the supervisory level, which obviously is a huge security flaw, because once you compromise that, you can do anything with the box. The software, the application software, is developed elsewhere and downloaded, as I mentioned. It supports many or numerous industrial standard proprietary communication protocols. Now, when I was doing my MSc, one of the lecturers said very dispassionately about these things. He said, they're very simple, stupid. He defined them as stupid. I say they're reliable. I can assure you, having brought up a power station, 20 tons an hour of steam, 160 bar, at 50 degrees superheat, when the top end, the supervisory layer has frozen on you, you like to know that that thing isn't going to freeze on you. And that has got some quite significant security implications, because they are so reliable that if anything goes wrong in a plant, it's the last thing anybody will blame. So if anybody attacks that, it could be up to 10 days before anybody looks at that box and says it could be that. And I believe, again, if you look at Ohio, I believe they replaced the pumps a couple of times before somebody clocked onto that something was cycling them on and off. I had on Connors Key Power Station, there was a firmware bug in one of the processors. And it took about 10 days before we got the manufacturers into eventually say, because you look at all the mechanical stuff, you look at all the electrical stuff, and no one will believe that that has actually glitched. Took them a bit longer than that to fix it, of course. Right. So, from an architecture point of view, the positives, there's very limited scope to hide malicious code. There's no hard disk, and it's a very, very compact memory map, direct memory addressing. Limited scope to inject malicious code. The communications protocols that I've described, on the whole, if you think about TCP/IP, you connect it, and you have all these services like web services, and they've all got to be supported at the other end. And if they're supported, and you can try, and you might get in, and you might be able to get in here and do something. These things are point to point. They're configured. This is a list of signals we're going to send. This is a list of signals we're going to receive. At one end, if not both ends, that is tied in and compiled into the code. And other than transmitting that list of signals, that protocol will do nothing else. And if you compare that to TCP/IP, for example, you can see that it's quite a different philosophical approach. Communication confined to transmission only, yes. No mechanism compiler run you can't download something, compile it, or run it on these PLC boxes. There's no environment to do that. Application software provides a barrier between comms and plant. Yes, if we go back to the processor model, built into that PLC, there are a set of rules which will say we can't start this pump unless we've got lube oil running, unless that discharge valve is closed. So all of those interlocks are built into that software. So even if you can send a malicious command to start a pump, generally speaking, the code in the application software in the PLC will stop you from doing that. But there are variables, trip levels, etc., which can be adjusted. And if you can get in there to adjust those out and wind them out to something which is an unsafe level and then send a command, it can be done. But it's difficult. The negatives. Top one, the engineers will assume plant failure rather than cyber attack. There's no real intrusion into detection. There's nothing to say on that box that it's been compromised. Password security at this level is weak. Now, most of the interaction with a PLC, etc., is from the supervisory level. You've got all your Windows, password protection, etc. But you can go in with a laptop on some of them, plug it in locally, and then, provided you've got the tool on your laptop, there's absolutely nothing stopping you going in and changing anything. And there's no verification between the PLC and the supervisory level. So anybody with an operator workstation who can get onto the network can plug it in and do what they want. So really you are relying on Windows security, and that's it. Same, anyone with an engineering interface can modify the PLC software, and anybody with an engineering software as an engineering interface could potentially modify the firmware. Now, of course, this changes from model to model and manufacturer to manufacturer, but as a general rule, there are things you have to be aware of. The model that I showed earlier with the 3 levels sort of breaks down a little bit. There's another technology where the instrumentation and the automation level are combined, and that's field bus. Interesting, because again, Stuxnet relied on it, the fact that the centrifuges were on a field bus network, Profibus. What you do with field bus is you build the intelligence into the physical devices. So this valve here would control the flow based on that pressure, maybe that level, but the actual algorithm that tells that valve where to go to and how to control the valve is built in at this level. The other model, that's all built into the PLC or the RTU level above. So you can get away, again, huge advantages. You can get away with a lot of the wiring. This is just a single communications bus which ties all those together. Much loved in the nuclear industry, because in a traditional process industry, generally your control cubicles have to go through a firewall, and that's expensive, and you've got masses of cables going through these firewalls. In the nuclear industry, you're taking through radiation barriers as well. So the nuclear industry. This technology came out in the mid-1990s. It's not been widely adopted, but there are 1 or 2 places. And centrifuges, surprise, surprise, are among them. There are 3 flavors. There's FIP, which is French, World FIP, which is derivation of that, Profibus, which is German. For years, the 2 of them were arguing. The Americans didn't want to get involved, and eventually they came out with Foundation Field Bus. The 2 big ones are Profibus and Foundation Field Bus. You don't see much FIP around. You see it on some French products, but you possibly heard of Profibus. Right, security and field bus. Much the same. The model I explained earlier with the PLC, nothing's really changed hugely. It just combines the automation layer with the field layer. And it's really, there's no significant impact on risk. Except if you look at Stuxnet, for this system to work, every device, every manufacturer has to register their device with a central library, which models and says what the behaviors of each of those devices are. And what you do is you register with this organization, and they give you a unique company ID, and then you add your model ID to that. And that was how Stuxnet knew that it was talking to a centrifuge, because it was scanning for the ID number that uniquely identified that as a centrifuge. Although Stuxnet was sort of pretty well universally distributed around the planet, and on a lot of control systems, it only actually activated. And that's how it knew when and where to activate. That's a little bit of trivia. Then we move up to the supervisory layer. A lot of this stuff is redundant. You have redundant networks, you have redundant. So I've just drawn the redundancy in. Most control systems rely on a database, Yokogawa being the exception. So something will happen down at the PLC level, and it will just put a pointer into the database saying, for example, I've gone into alarm, and then all of that data is extracted and pushed across the operator workstations. And the database is really effectively the interface between plant and supervisory layer. Supervisory layer, we have machines which can display trends, plant graphics, bar charts, alarms. Alarms are really, really important in driving process plant. All Windows machines these days. Go back to the 1980s, they relied hugely on DEC microvaxes for this sort of type of thing. You've also generally got a historian, which is another database which just collects years' worth of data. You've got various printers, and the engineering workstation here, which is where the engineer writes the application software. He can come in, debug his code. But when you're debugging software at this level, you're actually debugging it down at the PLC level. You download it into PLC level, and then you use tools on that to force signals, etc. So that's why this is so dangerous, because if you have access to that, you can do anything at the PLC level. And then at the right-hand side, if you want to interface with the management, with an IT system, you put a firewall and off you go. The beauty of this is the traffic that you're exchanging between the supervisory level and your IT system is absolutely known. And you can screw down the firewall just to let that small amount of traffic with very known parameters through and block everything else. So this form of security, you can get a very, very tight level of security using this model. So security and supervisory, they're ubiquity based on MS Windows. So all the security flaws that you get with Windows, so you've only got one manufacturer's product range to understand, and you have all things like USB ports, all the usual mechanisms. And as I hinted earlier, you've got also subject to the normal sort of Windows attack like ransomware. But the types of external traffic are small and well understood, so you can put in tight firewall rules. You've also got a level of high-quality intrusion detection. You can rely on the Windows type of intrusion detection. Problems with patching. Again, I come back to the Service Pack 2 story. Yokogawa again, if you want to do your Windows patching, you download your Windows patches from their website. They pre-test them and they release them. Single function, yes, this is quite important. You wouldn't put anything other than the software that you need to control the plant on this, so you wouldn't have email clients and things like that on any of this operational technology. Not if you were sensible anyway. So, how do you get a bit of malware in? Well, it's not going to be emailed in. It's got to come through that firewall. The other point I've made earlier is the engineering workstation hold all of that detailed information that you need to mount an EDOS attack. So that from a purely information security point of view, they are vulnerable. You'd be looking to get the information off there. So a quick recap. I've seen this diagram before, and I'm just showing you here how the risk or the vulnerability goes up, rather. The higher up the level, the layer you go. So, put into perspective. So, security inherent in the system. There are a large number of manufacturers out there, and I come back to this thing about Windows. If you're attacking an IT system, how many operating systems are there out there? Well, I can think of several dozen manufacturers who make this type of kit. So you've got a large amount of security through diversity. There are a lot of legacy systems. I'm still supporting, or have been supporting, some offshore oil platforms which are running microvaxes and OS2. Yeah, okay. Security through antiquity. Okay. Closed proprietary systems and protocols. There are dozens of these protocols. A lot of them are closed. And there are a lot of them on any installation. So you don't just need to know one protocol to launch attack. You probably need to understand in detail half a dozen. So again, there's security through obscurity. I know that the InfoSec world balk at these, but they're there, and they make life difficult. You have very high levels of physical security generally, and again, the communications traffic, we've spoken about that. So I'd like to bring the two bits together now. If you remember, we discussed to begin with the industry structure. We looked at the technology or the generic model. If we bring them together, and we can answer this question. Could the power grid or North Sea oil production be brought to standstill by cyber attack launched against power station production platforms? Any answers? I would say very unlikely. Yeah, that is a yes. Yes, it is. Yes. It's late. I was up at 4 o'clock this morning. Right. So we start off, crummy picture of a power station, but there you are. The thing I'd like to point out is it's got a fence around it. So we start off with good physical security. We can draw a physical and logical box around what we're looking at, which is quite useful. And if we look at it, we've got a boiler and a turbine hall. This is typically where your instrumentation layer would be. We've got a control center, CCR control, central control room. So the person who goes in there has to come through a layer of protection, come through the gate, get in through secure doors up to the control room, which is manned 24/7. And you've also got an equipment room, which is where all the PLCs would, and that's generally locked and access controlled. And if you look at this, I've sort of reproduced that diagram and showed where the various layers would be on that side. So really, if you want to get in there and do something at a cyber level, as I come back to the thing, there are easier ways to bring the plant down. If you're going to go in and do damage, it's difficult. So access to control equipment is highly controlled, and there are limited practical methods of doing anything. There's the concept in insider attack, USB stick dropped in the hope that somebody plugs it in, possible. And you might just get in through the firewall. So to add to that, you've got the security through diversity, antiquity, and obscurity. No two power stations are the same. The closest you will probably get is a Siemens power station. They tend to be very similar, and they tend to use their own control systems, etc. But a lot of them will have a DCS, which is by one manufacturer on one site, and then the other client wants somebody else's DCS. And then they'll have somebody else's gas turbine, and their gas turbine control panel will be different to the other person's, etc. And also an EDOS attack is difficult without the detailed understanding of how the plant is built and put together. Okay. So the probability of simultaneously shutting down 70-odd UK power stations is remote. Do you want to look suitably embarrassed? Right. So where would you attack? And I mean, we look at the Ukraine attack here. They didn't go after the power stations, individual power stations. They went after this bit, which was the national distribution. That's a bit to shut down. Because everything runs through there. And if you look at this, how the electricity, and it's very similar, the oil and gas is very similar. You have the production facilities, you have a large, wide-scale distribution, you then have your local distribution down to consumers. So, but there is a variant on this, and this is a remote-operated SCADA site. And here, if you like, we've taken the supervisory level and moved it off-site. And this obviously does add a security risk, because you've lost your physical security around the, well, not around the control room, but between the control, the link between the control room and the physical asset. And wind farms, water companies, etc. And to be honest, water companies are believe it or not, one of the most difficult to protect because just the nature of the architecture is very, very... there's a huge link between that and that you don't get the separation. Whereas if you look at the wind farm model, you generally, the remote operation is quite separately, physically separate and logically separated from the management information systems. So, in summary, the fundamental difference in approach between IT and OT security are the generic risks are different. It's PAIR versus CIA. Electrical, mechanical, and computer systems are treated very much as one, just variants on a theme. Information has no real value in the OT world, certainly not in the process industries, etc. we've discussed. And we've got to consider the difference between an EDOS and a DOS attack. A DOS attack really, emotionally, it would get people quite upset because there's an uncertainty about it. But really, in terms of its impact, it's probably no worse than a pump breakdown or something like that. Expertise does not automatically transfer from the IT to the OT worlds, or from one OT sector to another. I mean, I'm quite deliberately focusing on the bit of the OT world that I know and understand. I'm not talking about manufacturing here because it's not an area that I feel competent talking about. We've implicitly touched on two types of risk, the national infrastructure versus the single asset risk. So whether we're attacking individual power stations, which could be an attack if you want to target a particular company, but if you want to bring down an entire national infrastructure, that's not the way to go. Control system structure impact on security, yes. We've looked at the actual architecture as well and how the risk profile increases the further up the stack we go. And, well, instrumentation being the lowest and supervisory the highest. And we've added on how the complexity increases once we add a telemetry or SCADA system, remote SCADA system on. And that's it. Thank you very much. You sat through that all right.